This is the beginning of Module 3C, Moisture, Decant, Gradation, and Practice Problems. This module includes a moisture video, a decant video, a gradation video, and an example of a calculation problem. Determining the moisture content of an aggregate at the HMA plant is critical for quality control and production. Measurement of the moisture gives the QC technician valuable information regarding the condition of the aggregates and the possible effects on mixture production and performance. Also, the HMA plant operator must know the moisture content of all aggregate components daily and whenever the moisture content changes, so that the HMA plant can properly compensate for moisture during production. The following video will show the procedure for drying an aggregate sample.
Total evaporable moisture content of aggregate by drying, T255. To determine the moisture content in an aggregate by drying, first secure the sample that meets the minimum testing size requirements. Place the sample in the selected heat source, being careful not to lose any particles. Very rapid heating may cause some particles to explode, resulting in loss of particles. Dry the sample to constant mass. Constant mass is achieved when further drying causes less than 0.1% loss in mass. Once constant mass has been reached, bring the sample out and cool it to room temperature for its final weight.
As you just learned, aggregate samples are dried to a constant weight in an oven set at 230 degrees plus or minus 9, or in an electric skillet or over an open flame. Whether you calculate the percent of moisture or not, you must fully dry the sample. The dry sample weight is the starting point and the basis for calculations for the remaining tests on the aggregate. Let's proceed to the next step in the process, decant. Determination of materials finer than the number 200 sieve by washing is performed in accordance with AASHTO T11 and is known as decant. Materials finer than the number 200 sieve can be separated from larger particles much more efficiently and completely by wet sieving than through dry sieving. Normally, this test is used on the test sample prior to dry sieving by AASHTO T27, and the total amount passing the number 200 sieve is the combination of the wet sieving and dry sieving processes. Plain water is normally adequate to separate the material finer than the number 200 sieve from the coarser material with most aggregates.
Materials finer than the number 200 sieve in mineral aggregates by washing, T11. Be sure the sample has been dried to constant mass. Place the sample in a teared out container and record the weight. Add sufficient water to cover the sample and add a wetting agent to the water. This is procedure B. Procedure A is without the use of a wetting agent. Agitate the sample with sufficient vigor to result in complete separation of all particles finer than the number 200 sieve from the coarser particles, and to bring the fine material into suspension. The use of a large spoon or other similar tool has been found satisfactory. Immediately, pour the wash water containing the suspended and dissolved solids over the nested sieves, arranged with the coarser sieve on top. Add a second charge of water without the wetting agent to the sample in the container, agitate, and decant as before. Repeat this operation until the wash water is clear. Place the washed material in a container sufficient for drying. All flushing of the material should be done over the number 200 sieve. Place the material retained on the guard sieve back into the wash sample and gently flush the remaining material on the number 200 sieve back into the sample as well. Dry the wash sample in a 110 degree plus or minus 5 degrees Celsius oven until constant mass is achieved. Once constant mass is achieved, take the sample, place it in front of a fan until it's cooled to room temperature before taking your final weight.
Continuing with Module 3C, let's discuss gradation. After completion of the decant, the material is dried to a constant weight, weighed and recorded, and then placed into the top of a set of nested sieves. Depending on the type of sample, an appropriate shaker and sieve shall be selected for the shaking procedure. Every effort should be made to avoid overloading the sieves.
Sieve analysis of fine and coarse aggregates, T27. Be sure the sample has been dried to constant mass and cooled to room temperature. Record the initial weight before placing the aggregate in the nest of sieves. To avoid sieve overload, the sample may be split into 2 or more portions, sieving each portion individually. Agitate the sieves by mechanical apparatus for a sufficient period that meets the criteria for adequate sieving. Once the agitation is complete, weigh the material retained on each sieve and record the weight. When cleaning each sieve, take care to not damage the sieve. Record the weight. Here I place the material in a separate pan so that my pan is always zeroed out before going to the next sieve. Lightly tapping with a scraper helps get the rocks out from between the sieves without damaging. Holding the sieve up against a white background helps to see whether or not all rocks have been cleared from the sieve.
In this final segment of Module 3C, I will guide you through a practice problem showing you the calculations for moisture decant and gradation. Since this is all pre-recorded, you're encouraged to follow along and then to pause the video at appropriate steps so that you can perform the calculations on your own. You will need the separate ICAT in-class problems document for this section. Page 1 and 2 of your in-class problem set handout should look something like this. We will follow the steps shown on this slide. The look of your handout will vary slightly from the following slides, but the numbers and calculations all match. After reducing your sample to test size, the first step is to dry the sample and to calculate the percent moisture. The formula for percent moisture is shown here. Wet minus dry divided by dry times 100. The wet weight and dry weight are highlighted in yellow. Use the weights in the formula to perform the calculation. Pause the video while you work this step on your own. The answer is on the next slide. The percent moisture is 0.8%. If you're trying to memorize this formula, the key to this formula is to remember to divide by the dry weight and not the wet weight. This final dry weight of 6678.1 is critical. All of the remaining calculations for decant and gradation are based on this dry weight. This is a full view of the worksheet showing the dry weight of the sample, 6678.1, and the weights retained on each of the sieves. The next step is to determine the applicable specification and to enter it in the percent required column. You can just follow along here. Your in-class handout does not include the specification column. The specifications for number 8 coarse aggregate are in 904.03. Transferring the specifications to the worksheet yields the following. Again, just follow along here. There's no room on your classroom handout for the percent required column. For 8s, the 1-inch sieve is required to have 100% passing. The 3/4 inch sieve is required to have 75 to 95% passing. The decant requirement of 0 to 3.0% comes from the next to the last row of the specification table in 904.03, labeled decant parentheses non-PCC, meaning aggregate not used in Portland cement concrete. In step 2, we can calculate the decant. The formula is shown here. If you're trying to memorize this formula, note that the amount of material removed by decant is divided by the original dry weight of the sample, in this case 6678.1 grams. The original dry weight of the sample is 6678.1. The dry weight of the sample after decant is 6564.3 grams. Pause the video while you calculate the decant percentage on your own. The answer is on the next slide. The percent of material washed through the number 200 sieve by decant is 1.7%. The next slide shows the formula in a format that matches your handout. Again, showing that the percent of material washed through the number 200 sieve by Decant is 1.7%. Step 3 begins the process of calculating gradation by computing the weight passing for each sieve. You are given the weight retained on each applicable sieve after gradation testing. Use the weight retained to calculate the weight passing each sieve. The starting dry weight of 6678.1 minus the weight retained on the 1-inch sieve of 0 grams equals the weight passing the 1-inch sieve of 6678.1 grams. Next, take the weight passing the 1-inch sieve of 6678.1 grams minus the weight retained on the 3/4 inch sieve of 720.9 grams to obtain the weight passing the 3/4 inch sieve of 5957.2 grams. Work your way down the weight passing column by following the same process for each sieve. Pause the video while you work this step on your own. The answer is on the next slide. This slide shows the weight passing each sieve. Next, calculate the percent passing each sieve. Take the weight passing each sieve divided by the original dry sample weight of 6678.1 grams times 100. For the 1-inch sieve, the weight passing is 6678.1 grams divided by the total dry sample weight of 6678.1 grams times 100 equals 100%. For the 3/4 inch sieve, the weight passing is 5957.2 grams divided by the total dry sample weight of 6678.1 grams times 100 equals 89.2%. Calculate the percent passing to the nearest 0.1% for the remaining sieves. Pause the video while you work this step on your own. The answer is on the next slide. The percent passing each sieve is shown here. In step 5, let's compare the results with the specifications. Looking at the percent passing and the percent required by specification column, compare the results with the specifications. Does the sample pass, meaning it meets the specification tolerances, or does it fail to meet the specification requirements? Comparing the percent passing column shown in blue with the percent required column shown in red, line by line, sieve by sieve, we see that the results are within the percent required in the specifications. Therefore, we would say that this sample passes the specifications. Lastly, let's compute the percent error for our example test. AASHTO T27 requires us to determine if this was a valid test. T27 requires us to perform calculations to assure that no more than 0.3% of the sample was lost during testing. How do you lose the sample during testing? Well, some losses are due to sloppy technique and some are inherent. Dropping rocks and not picking them up during handling is sloppy work. Not cleaning your sieves consistently is sloppy work. Having a few sand grains lodged in the perimeter of a sand sieve is inherently going to happen at times. So the 0.3% loss is an upper limit, and you should strive to develop good laboratory habits so that you never approach that limit. The formula for determination of the validity of the test is shown below. Note again that everything in the calculation is based on the original dry weight of the sample. The summation of the weights measured means that you add up all the individual weights obtained and recorded during testing. You weighed the amount of material in every sieve plus the pan, so add up those weights. As shown here in purple after the sigma, the total of the individual weights retained on each sieve plus the pan was 6,553.2 grams. Additionally, you indirectly measured the amount of material lost by decant, 113.8 grams. So pause the video while you work this step on your own. The answer is on the next two slides. The total summation of all weights measured is 6,553.2 grams plus 113.8 grams equals 6,667.0 grams. The total dry starting sample weight was 6678.1 grams. The summation of weights measured during testing, including all sieves plus the pan plus the decant, was 6667.0 grams. Plugging into the formula, a total of 0.2% was lost during testing. Since 0.2% does not exceed 0.3%, this is a valid test. Learning test methods, techniques, and calculations are important steps in your journey to becoming an excellent technician. The unwritten rule for an excellent technician is to be uniform and consistent in everything that you do. When you get a failing test or an unexpected result, you want to be confident that the material changed, not that you were inconsistent in your procedures. This is the end of modules 3C for moisture, decant, gradation, and the practice problem. You can now navigate to module 3D and then module 3E for the remaining topics and aggregates.